Spherical mirror. You must have seen the mirrors displayed in the laughing chamber in a fair. You have been surely amazed to see your face being distorted in these mirrors. Do you know why does this happen? This happens because these mirrors are different from the mirrors we have at home. The mirrors in the laughing chamber are curved. The images formed by curved mirrors are different from those formed by plain mirrors, due to which we do not see the familiar images in these mirrors. The rear view mirrors in cars, which enable drivers to see the vehicles coming from behind, are curved mirrors. Come, let us know more about these mirrors by performing an activity. Activity: take a rubber ball and cut it into two parts. Let's name these parts as A and B. Now, observe the two parts of the rubber ball. We see that each of the two parts has two types of surfaces. Generally, spherical mirrors are parts of a hollow glass sphere like the part B. The inner or outer surface of this part is coated with a shiny substance to produce a spherical mirror. Reflection of light takes place either from its outer or inner surface. Thus, there are two types of spherical mirrors. They are concave mirror and convex mirror. If the inner surface of the spherical mirror is the reflecting surface, then it is called a concave mirror. Whereas, if the outer surface of the spherical mirror is the reflecting surface, then it is called a convex mirror. Before studying about these mirrors in detail, let us first know the terms related to spherical mirrors. Terms related to spherical mirrors. Pole. The center of the mirror surface is called its pole. P is the pole of the mirror shown here. Center of curvature. The center of the sphere of which the mirror is a part is called the center of curvature. C is the center of curvature of the mirror shown here. Radius of curvature. The radius of the sphere of which the mirror is a part is called the radius of curvature of the mirror. The length CP or CA is the radius of curvature of the mirror. Principal axis. The straight line passing through the pole and center of curvature of the mirror is called its principal axis. PM is the principal axis of the mirror. Principal focus. Incident rays which are parallel to the principal axis of a concave mirror, after reflection from the mirror, meet at a particular point in front of the mirror on the principal axis. This point is called the principal focus of the concave mirror. F is the principal focus of the concave mirror. The principal focus of the concave mirror is real. In the case of convex mirror, incident rays parallel to the principal axis after reflection appear to come from a particular point behind the mirror lying on the principal axis. This point is called the principal focus of the convex mirror. F is the principal focus of the convex mirror. The principal focus of the convex mirror is virtual. Focal length. The distance between the pole and the principal focus of the mirror is called the focal length. Small f. This distance is half of the radius of curvature of the mirror. After understanding the terms related to spherical mirrors, let us now move to the next part. Drawing the reflected rays. Let us perform an activity. One figure is shown on this drawing board. As we can see, Mn is a spherical mirror. Ray AQ is incident on the mirror. C is the center of curvature of the mirror Mn. Now, can you determine the direction that an incident ray will take after reflection from a spherical mirror? Let us first find out the angle of incidence. To do so, let us join point C and point Q. Now, CQ is nothing but the radius and therefore is perpendicular to the mirror at Q. Thus, angle AQC is the angle of incidence. Let us measure this angle using protractor. It is 45 degrees. According to the laws of reflection, angle of incidence and angle of reflection are of the same measure. Thus, the angle of reflection will also be 45 degrees. Let us now draw a ray making an angle of 45 degrees with CQ. Let's name this ray as QB. This is the reflected ray. According to the laws of reflection, the incident ray and the reflected ray are on the opposite sides of the normal to the reflecting surface at the point of incidence. Thus, ray QB will have this direction. The images produced by spherical mirrors can be studied by drawing ray diagrams. But do you know what is a ray diagram? A ray diagram is the depiction of the path taken by light rays. To draw a ray diagram, we use some rules which are based on the laws of reflection of light. Come, let us study these rules. Rule 1. If an incident ray is parallel to the principal axis, then the reflected ray passes through the principal focus. Rule 2. If an incident ray passes through the principal focus of the mirror, then the reflected ray is parallel to the principal axis. Rule 3. If an incident ray passes through the center of curvature of the mirror, then the reflected ray traces the same path back. Come, let us now understand how the images are formed by a concave mirror. Images formed by a concave mirror. Activity. To perform this activity, we need glass lamp, 2 cardboard boxes, large cardboard sheet, white paper, concave mirror, meter ruler, and wooden block. First, take the cardboard box to hold the light source, that is glass lamp. Cut off its upper side and place the lamp inside the box. Now cut out an arrow-shaped slit from one side of the box so that we get an arrow-shaped light source. Let us now make a screen of size 20 cm by 30 cm by sticking a white paper on the cardboard sheet. Set it up vertically with the help of the wooden block. Take another cardboard box and make a slit on its top surface. In this slit, fix the mirror vertically. Now let us place the screen near a window and place the mirror in front of it such that the image of the sun or some faraway distant object forms clearly on the screen. At this distance, we get clear image of the faraway object. Let us now measure the distance between the screen and the mirror. This distance is the focal length of the mirror. It is 15 centimeter. Now, in a dark room, place the mirror near the 0 mark on the meter scale. Place the screen in front of the mirror and place the source of light in between the mirror and screen so that the distance between the mirror and the light source is little more than the focal length of the mirror, that is, more than 15 centimeter. Now let us obtain the clear image of the light source on the screen by moving the screen along the meter scale and perpendicular to it. At this distance, we get the clear image of source. The image is inverted and larger than the source. The image of the source is obtained on the screen, and thus it is a real image. Now let us move the source away from the mirror so that the distance between the mirror and light source is greater than twice the focal length of the mirror. That is greater than 30 centimeter. Let's move the screen again towards the mirror and along the meter scale. At this distance from the mirror, we get the clear image of source. It is inverted, smaller than the source, and real. Come, let us now study image formation by a concave mirror when an object is placed at different distances with the help of ray diagrams. As shown here, an object AB is placed between the focus and the center of curvature of the concave mirror MN. The incident ray AQ is starting from A and passing through the focus F of the concave mirror. It becomes parallel to the principal axis after reflection and returns along QR. Another incident ray AS is parallel to the axis, which after reflection passes through the focus F and returns along the path ST. It cuts the reflected ray QR at point A1. The point B is situated on the principal axis, and so its image will also be on the axis and will be directly above A1. Thus, the image of B is at B1. The images of points between A and B will be formed between points A1 and B1. Thus, the image of object AB is A1, B1. From this, we see that when the object is placed between the focus and the center of curvature of the concave mirror, the image is formed beyond the center of curvature. This image is larger than the object and it is inverted. As the reflected rays actually cross each other, the image formed is a real image and can be obtained on a screen. Let us try another position of object and see where does the image form. As shown here, an object AB is placed between the pole and the focus of the concave mirror MN. The incident ray AQ is parallel to the principal axis, which after reflection passes through the focus F. Another incident ray AS is in the direction joining A with the center of curvature C, which gets reflected back along the same path. The two reflected rays do not meet each other. However, if they are produced backwards, they appear to intersect at point A1 behind the mirror. From this, we see that when the object is placed between the pole and the focus of the concave mirror, the image is formed behind the mirror. The image is erect and larger than the object. As the reflected rays do not actually meet but appear to come together behind the mirror, the image is a virtual image. The position and type of the image produced by a concave mirror when an object is placed at different distances from it are given in the table. Out of these positions, we have studied the position and type of images formed by a concave mirror when the object is placed between focus and center of curvature and between pole and focus. Come, let us now determine the position and types of images for other positions of the object and tally answers with the information given in the table. Image formed by a convex mirror. Consider an object AB kept in front of a convex mirror MN anywhere between pole P and infinity. A ray of light AQ traveling parallel to the principal axis is incident on the mirror. It gets reflected as a ray QT. According to the rules, the ray appears to come from focus F. The other ray, AR, traveling towards the center of curvature C, gets reflected along the incident path as ray RA. The two reflected rays, QT and RA, do not actually meet at a point, but appear to meet at point A1 behind the convex mirror. It is clear that the image is smaller than the object, behind the mirror, and erect. As the reflected rays do not actually cross one another, the image is a virtual image. The nature of the image formed by a convex mirror does not depend on the distance of the object from the mirror. These images are always virtual, smaller than the object, and situated behind the mirror. After learning image formation, let us now understand divergence and convergence of light.